Certainly. Black holes are fascinating objects in the universe, characterized by their extremely strong gravitational pull that nothing, not even light, can escape from within a certain region known as the event horizon. Here are some key points about black holes. Formation: black holes are formed when massive stars run out of fuel and collapse under their own gravity. The collapse is so intense that it creates a singularity, a point in space where gravitational forces are infinitely strong. Sizes: black holes come in different sizes. Stellar black holes are formed from collapsing massive stars and can have a mass up to about 20 times that of the Sun. Supermassive black holes, found at the centers of most galaxies, can have masses millions or even billions of times that of the Sun. Event horizon: the event horizon is the boundary around a black hole beyond which nothing can escape. Once something crosses this boundary, including light, it is pulled inexorably toward the singularity. Singularity: at the center of a black hole lies the singularity, a point of infinite density where the laws of physics as we currently understand them break down. Our current understanding cannot describe the state of matter and energy at this point. Spacetime distortion: the immense gravitational pull of a black hole causes a significant distortion in the fabric of spacetime. This effect is predicted by Einstein's theory of general relativity. No-hair theorem: the no-hair theorem suggests that black holes can be described by just three properties: mass, electric charge, and angular momentum. All other information about the matter that formed the black hole is lost. Hawking radiation, proposed by physicist Stephen Hawking. Hawking radiation is a theoretical prediction that suggests black holes can emit radiation and gradually lose mass over time. This process is due to quantum effects near the event horizon. Interstellar influence: black holes play a crucial role in the dynamics of galaxies. Supermassive black holes are thought to be at the centers of most galaxies, and their gravitational influence can affect the orbits and behaviors of surrounding stars. Types of black holes: stellar black holes, formed from the collapse of massive stars. These black holes typically have a mass between 3 and 10 times that of the Sun. Intermediate black holes: the existence of intermediate black holes with masses between 100 and 1,000 times that of the Sun is theorized, but not yet conclusively proven. Supermassive black holes, found at the centers of most galaxies, including our own Milky Way. These black holes have masses ranging from hundreds of thousands to billions of times that of the Sun. Formation of black holes: black holes form when massive stars exhaust their nuclear fuel and are no longer able to support their own gravitational collapse. This collapse results in a singularity surrounded by an event horizon. Hawking radiation. Proposed by physicist Stephen Hawking in 1974, Hawking radiation is a theoretical prediction that black holes can emit radiation and gradually lose mass over time. This process involves the creation of particle-antiparticle pairs near the event horizon, with one particle falling into the black hole and the other escaping as radiation. Observing black holes. Black holes themselves are challenging to observe directly because they do not emit light. However, their presence can be inferred by observing the effects of their gravity on nearby stars and gas. The Event Horizon Telescope, EHT, made headlines by capturing the first-ever image of the event horizon of a black hole in the galaxy M87. Gravitational waves. Black hole mergers and other extreme astrophysical events can produce gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo collaborations have successfully detected these waves, opening a new era in astronomy. Information paradox. The fate of information that falls into a black hole is a topic of intense theoretical debate. According to classical physics, information that falls into a black hole is lost forever, violating the principles of quantum mechanics. This is known as the information paradox. White holes and wormholes. While black holes are regions where nothing can escape, hypothetical objects called white holes are theorized to be regions where nothing can enter. Wormholes, also speculative, are bridges or tunnels that could connect different points in spacetime. Microscopic black holes. Theoretical physicists have proposed the existence of tiny, primordial black holes that could have formed in the early universe. These micro-black holes, if they exist, would be much smaller than stellar black holes. Black hole thermodynamics. Analogous to the laws of thermodynamics, black hole thermodynamics describes the relationships between black hole properties such as mass, temperature, and entropy. Future studies. Ongoing and future missions, such as the Laser Interferometer Space Antenna, LISA, will continue to explore the gravitational wave universe, providing more insights into the behavior and properties of black holes. Accretion disks. When matter falls into a black hole, it often forms a rotating disk known as an accretion disk. The intense gravitational forces cause the material in the disk to heat up and emit X-rays, making these systems detectable by telescopes that observe in the X-ray spectrum. Quasars and active galactic nuclei, AGN. Many galaxies, particularly those with supermassive black holes at their centers, exhibit high-energy phenomena known as quasars or active galactic nuclei. These are incredibly luminous and are powered by the accretion of material onto the black hole. Spin. Black holes can rotate, and their spin is a crucial parameter in understanding their properties. The spin affects the size and shape of the event horizon and influences the behavior of matter around the black hole. Kerr black holes. A rotating black hole is described by the Kerr solution in general relativity, named after physicist Roy Kerr. The event horizon of a rotating black hole is more complex than that of a non-rotating, Schwarzschild, black hole. Naked singularities. The cosmic censorship hypothesis suggests that singularities within black holes are always hidden within the event horizon, preventing them from being observed directly. However, the existence of naked singularities, not hidden by an event horizon, is a topic of debate in theoretical physics. Tidal forces. The gravitational forces near a black hole can be so strong that they cause extreme tidal forces. These tidal forces can stretch and deform objects, a phenomenon known as spaghettification. Primordial black holes. There is speculation about the existence of primordial black holes, which could have formed in the early universe through different mechanisms than the collapse of massive stars. These black holes could have much smaller masses than stellar black holes. Black hole information paradox. The question of what happens to information that falls into a black hole is a central topic in theoretical physics. The apparent conflict between quantum mechanics and general relativity regarding the preservation of information is known as the black hole information paradox. Fuzzballs and firewall paradox. Some theoretical physicists propose the idea of fuzzballs, which suggests that what we perceive as a black hole could be a cloud of strings. The firewall paradox challenges traditional views on the nature of the event horizon and the smooth passage of objects through it. Black hole mergers. LIGO and Virgo collaborations have observed gravitational waves from the mergers of stellar mass black holes. These events release a tremendous amount of energy in the form of gravitational radiation. Astrophysical jets. Black holes, especially those with accretion disks, can launch powerful jets of particles and radiation into space. These jets can span vast distances and influence the surrounding interstellar medium. Quantum gravity and black holes. Understanding black holes at the quantum level requires reconciling quantum mechanics with general relativity, a challenge that has led to the exploration of theories like loop quantum gravity and string theory.